Hello and welcome. My name is Nick Brimley, and I'm the Marketing Director for the Slag Cement Association. I will be moderating today's webinar, Low Calcium Slag Cement, a Potential Solution to Promote Circular Economy in the Management of Copper Mine Tailings. Our speaker today is Arash Nikvar-Hassani. Arash is a geological engineer in the Power and Dams Group at Stantec. He is also an adjunct scholar in the Sustainable Materials and Recycling Technologies Group at the University of Arizona. He has published over 24 peer-reviewed papers and was also a research winner for the 2022 Slag, Cement, and Sustainable Concrete Awards. If you have any questions during the webinar, we ask all attendees to please use the Q&A feature, and we'll get to your questions at the end. And with that, I will hand it off to you, Arash.
Thank you, Nick, for the introduction. Hello, everybody. Thank you for attending the webinar, and thanks to the Slag Cement Association for this opportunity. Okay, let me share my screen, and then we can go from there. Okay, could you confirm that you see my screen, Nick?
Do not see your presentation yet.
Okay, let me see. How about now?
Oh, perfect. You can see it.
So as Nick mentioned, today's talk is about using the slag cement as a potential solution to recycle mine tailings and promote circular economy in the construction materials industry. So the outline of the topic is we will start with some introduction about the topic, and then we'll show you the research approach, some of the material properties, how we prepare the laboratory scale specimens, and then we will have some results and discussion, and at the end we will provide some conclusion and what future work needs to be done. So as an introduction, with the population growth and urban development, the needs for construction material has risen significantly, especially in terms of cementitious material. And as a conventional cementitious material, we should talk about ordinary Portland cement. The demand for this material is significantly increased during the last decades. If we want, as engineers, we want to give some numbers about this, like demand. So you see from this graph that the rise of demand is significantly increased since 2010, and in 2022 only 95 million tons of Portland cement and Missouri cements in the United States is produced. So it's really a big number. But is it a problem? The problem is here. Yes, there is a problem. To produce 1 ton of OPC cement, normally we use 1.5 tons of raw material. This means we need to do mining in the quarries and produce raw materials needed for the Portland cement, and that brings CO2 emissions to the atmosphere. Just the production of the OPC, especially in the burning of the limestone, we will have 1 ton of CO2 to the atmosphere. Which means we are responsible for 8% of the CO2 emission to the atmosphere, just the cement industry. So if we continue like the current condition, actually nowadays it's better, but if we consider the current condition, this number is high and we need the goal of 2050 that we need to be sustainable in every part of the industry. So we need to think about this part and try to reduce the number. So what can we do? There are some tailings around the world that mining industry produces annually. So as probably all of you are aware, the mining industry generates 2 types of tailings. So first, during the excavation, we have some material that are not desirable. So we send them to the tailing dams as rocks and gravels. And the ore or deposit will be sent to the mineral processing section, and that will be processed. The precious material will be taken out, and the rest of them as a fine powder will send to the tailing pounds. And those are fine powders containing elements such as silica, aluminum, calcium, sometimes iron, and also a lot of heavy metals inside those powders that are carcinogenic. And in some cases, like let's say in some states like Arizona, Texas, when the weather is hot and dry, and then with the winds coming up, and those heavy metals can go to the air and then make the people around the dam it brings health and safety issues. Beside that, we will have the rain, and the heavy metals will leach down to the underground and pollute the underground. Of course, the engineers will try to design tailing dams that prevent these issues. But anyway, we are like putting the hazardous materials open to the space. Just to give some numbers about this issue, so generally 1.6 billion metric tons of mineral processing waste are produced each year just in the United States. And after processing of, like, for example, copper, 2.5 million tons of slag and 1.5 million tons of slag tailings produces annually. So is there any issue that we are sending the tailings, like these waste material, to the tailing dams? Yes. For example, if you see a picture, a tailing dam failed in the Brazil, and tons of materials flowed to the downstream side, and like you see the surrounding neighborhoods, like in the surrounding towns, they are all like they're stated. And for example, if I want to talk about this special case, BHP is facing about $44 billion of lawsuits in the UK, which was about 2015. I didn't check the news, that's what happened. But anyway, if we want to give some statistics about the mine tailing failures, so this graph shows the failures from 1915 to 2019. And you see at least annually we have one failure. And the tailings that like flow down, it can start from minimum of 5 million cubic metric to up to 45 million cubic metric. And you see that's a huge amount of materials flowing down. And as I said, these tailings have heavy metals inside it that are not good for health and safety. And also, like we are going to have all the like surrounding towns, they are not going to be habitable for some time. And the dust issue is there too. So why these, and just give some idea why these tailing failures happen. Like there are some statistics here. So for example, for the cause of failures, the type of the construction they do can cause the failures. The biggest number is for the biggest failure reason is overtopping. The construction method, the biggest one that brings the failure is the upstream method. Or normally the failures mostly happen in active mines because there is actively water going to the system, pore water pressure is increasing in the tailing dam, and failures are happening, just as an example. And if we want to talk about human loss, luckily like 80% of the time is zero, but based on the statistics, 8% of the time, 1 to 10 people. And again, we need to prevent all these. Now, if we want to talk about having all these said, now let's see how the industry works in mining like how the industry works, how the business model is. So in terms of like mining industry, we have the processing of raw materials. So first we do the exploration and mining. This is a general graph actually, but if we want to specifically talk about mining, we have the exploration of the mining, then we have this excavation done, and then we send the material to process, then the processing will done, parts will manufacture. At the end of the cycle, we have the tailings generated and send it to the landfill. So it's a kind of like linear production chain that is happening, and the waste generated sends to the landfills, and we talked that all those issues can happen. But But truly, is there any way to prevent this waste generation, or can we do something with the waste? The circular business model talks about trying to keep the material in the loop as much as you can and try to benefit from the material. So nowadays they try to use even tailings to again recover the material that they didn't have the technology before, and now they have the technology. They can try to recycle, for example, the critical elements. But again, even after do all these recyclings, we have a mine tailing that is generated, and we can't do anything with that. So should we send it to the landfills? The circular business model says we can even do the recycling of industrial residuals. So even the waste generated, and then we try to recycle that waste, we can recycle the industrial residuals too. So in terms of the mine tailings and slag, what we can do is we try to produce some construction material with that. And do we have any solution for that? Because those are just the powders that we send it to landfill. Yeah, there is a technology called geopolymerization that we can use to produce construction material in like bricks or concrete with the mine tailings. But what is geopolymerization? Geopolymerization basically is transforming the aluminum silicate materials through some chemical reaction using the alkali activators or nowadays acidic activators and produce something called geopolymer. So we have the mine tailings. They are normally rich in silica and alumina elements, and then we have alkali activators. These days there are some research being done using acidic activators. So in terms of alkali activators, we could name like sodium hydroxide, potassium hydroxide, and in terms of acidic activators, we could talk about phosphoric acid. And then we have the water, so we mix them and we produce this geopolymer paste. And then we have some curing happening on this paste, and then we will have the construction material, and we are going to talk about it. But what is this paste? This paste is a 3D network of silica, alumina, polymer network, and that is very strong in durability. Very strong in durability. And if we want to talk about other benefits of geopolymerization, we would say we have abundant raw material sources. As I said, mine tailings are the simple one, and we have other tailings in the industry, but that they have high amount of silica and alumina, but they are not the scope of this work. So we are just talking about the slag and mine tailings. The good thing about geopolymerization is that the mechanical strength development is rapid in compared to the conventional cementitious material. It significantly stabilizes toxic materials inside this polymer network, and the energy consumption and greenhouse gas emission will reduce significantly because we spend huge amount of energy to just burn, to process the clinker, burn the limestone and produce the clinker. And here we are like trying to emit those type of energy consumptions. So why brick? This research is mostly about bricks. So why we need to produce bricks, and is it important? Is it a big industry? Well, bricks have been widely used in construction industry, and generally the procedure to produce bricks is, again, we do some mining operations and we try to mostly excavate clay materials, and we use high temperature kiln firing to produce the bricks. Natural resources like clay is limited worldwide, and this CO2 emission is also, again, producing problems to the environment. So is there a big number of bricks produced and used in the industry? Yes. So just in the US, if you see the statistics from 2014 to 2022, the number of the bricks produced is a little bit decreased, not significantly, but just in 2023, it's projected to produce $5.8 billion of bricks. That's a big market for the bricks. So probably we can do something to make it sustainable. So if we want to look and see what numbers we should look when we are producing the bricks, based on the ASTM specifications, we are talking about 21 megapascal of the minimum UCS in 28 days, and the maximum water absorption of 16%. This means that the bricks we produce currently with the conventional methods meet this requirement. But if we want to produce the new bricks using the geopolymerization technology, we need to consider and make sure to achieve these goals. So to see if we can, we follow this research process, research approach. We did the study in both macro scale, and we did the study in non-scale. In the micro scale, we produced the samples and we did a bunch of testings on them. So we did a uniaxial compression test, water absorption test to see how much water they are absorbing during time. We tested the bricks for wet and dry cycles, and also freeze and thaw for the cold temperatures. At the end, we did some environmental testings on the brick to make sure that the raw material, like mine tailing that have heavy metals, are we able to stabilize them inside the polymer network of geopolymers, and how successful we are. Then we did some microscale and non-scale study to make sure how the microstructure is changing with the chemical reaction we are doing on the mine tailings. So first, let's talk about a little bit about the material by itself. So the material we are using here is mine tailing and slag. And if you check their distribution, the particle size distribution, we are seeing that they are pretty fine material. And the slag, basically, we didn't use any commercial slag from the industry that is available. We got the slag tailings, like the stones, from the mining landfills, and we powdered them in the lab. So there is no other process happened on the slag cement, slag powder. And you see the material is mostly less than 100 micron in terms of the sizings. Then we did some chemical analysis on the tailings and see what are the properties. And as we discussed, the mine tailings and slag are high in silica and alumina. This gives us some potential for producing some good cementitious materials. Slag also is high in iron, and we have some calcium, but the amount of the calcium is very low. But compared to the mine tailing, we have higher amount of calcium. The microstructure of mine tailing and slag looks like you see at the 300 micron scale. Both the slag and mine tailings have regular shapes and some kind of sharp edges. And the XRD pattern of the mine tailing and slag shows very crystalline material. When the materials are crystalline, it's hard to dissolve the silica and alumina from the material because they are the silica and alumina are engaged in very strong crystals. And to break those crystals, we need heavy alkaline activators or acidic activators, which we are going to talk about. To prepare the specimens, we followed this procedure, very simple. So we mix the mine tailing with the slag at a desirable ratio. The reason we use the slag, we are going to talk about it later, but the amount of the slag we use, we try to use it as minimum because the goal was the slag is kind of like an improvement for us in this study. The slag helping us to produce better and durable material. So the maximum amount of the ratio was went toward the mine tailings. Then we mix the mine tailing, this combination with sodium hydroxide as alkaline activator. Then we added some sodium silicate to balance the silica and alumina ions. Then we mix them and compact them inside the mold. Then we cure them in the oven. And at the end, we have the bricks. And we did the testings on the brick samples. So this graph, now we are going to discuss some of the results. This graph shows the sodium hydroxide alkalinity. So if we use 10 mole or 15 mole, And then we use the SS over SH ratio. So the blue lines or blue bars shows for the 10 mole sodium hydroxide, and the green one shows for 15. So it's higher alkalinity. And you see, by increasing the alkalinity of the solution, alkaline activator, we are having a better and stronger geopolymer. And this shows the UCS for 7 days. So you see, for example, at this combination, and the maximum sodium hydroxide molarity, we are reaching about 22 megapascal just in 7 days. That's why we are talking about like geopolymers are rapid in strength development. So this graph shows us that two things. First, by increasing the sodium hydroxide molarity, the UCS is increasing, the strength of the material is higher, and also the density of the material is higher. That means the material is denser, the microstructure is more compact, and the material is heavier. But what happens? Are we good now? No, because here we didn't use any slag. This graph shows with only mine tailings. And what happened really? I will show you this figure and then we will go back to the chart. So what happened really? That even the maximum UCS sample, when we took it out after the testing and exposed it to the water, the material just decomposed. What does this mean? This means geopolymer is not good? No. This means that actually there was no geopolymerization, not much geopolymerization happening. And that was basically, you had the silica gels that holding the mine tailing particles together. And what is the reason? Two things. First, as we discussed, the mine tailings are very crystalline material with the XRD patterns we show. Then we try these materials, these tailings, we brought it from a abandoned tailing dam. That means the dam closed 20 years ago, and a lot of weathering happened on these tailings. And when we checked to see after 24 hours of submerging these powders inside the alkaline active liquid, how much silica and alumina we can get, and then compare it with the active mine tailings in the industry, we saw, wow, there is a big difference. So the mine tailing we had, after 24 hours, we only able to take out 16% of the silica from the material and 17% aluminum. However, compared to the data we have for active mine, if you get the material from an active mine, then you can get 61% of silica and 45% of aluminum. If you have a huge amount of silica and alumina dissolving from the raw material, that means you are able to produce amorphous material. But otherwise, if your mine tailings is very crystalline, you're not going to be able to get enough silica and alumina materials from the tailing dams, and you're not going to be able to produce polymer networks, which we call it geopolymer. So to help with this, we said, okay, we can use some kind of like active waste material. And that's how we went and used slag material, which helped us in this study. And just, you're going to see the results later on, but just give you an example. This is only with 10% slag. You see the material is very durable. The integrity of the sample is there. Even after we crush the sample and we put just the crushed sample, so even the core of the material is exposed to the water, it's still keeping its integrity. So now we try to see, okay, slag is good, so how much slag we need to add? We check the slag amount and we use the 0. We used 5, 10, 15, 20, but here just show you some example of the data. We show 10% and 20% of the slag. When we are increasing the slag, the UCS is increasing. That's good. That means we can get more silica and alumina from the slag because the slag is a very high reactive material. It experiences a high temperature in the smelting process. So it's already amorphous material, and you can easily take this silica and alumina from the slag out, and you can produce this geopolymer. And also, because the slag is a heavy material, is the density of the slag, specific gravity of the slag is much higher compared to the mine tailing, the bulk unit density of the samples are also increasing. So how much slag we should use? Generally, we decided to keep this slag minimum 10%, because more slag is good, but the goal of this study was to try to recycle more of the mine tailings. So we have some microstructure studies along with the UCS. So each time I'm talking about the micro scale studies, then we are going to detail and see how the microstructure is changing. So this graph shows you with 0% slag, then 10% slag, and then 20% slag. And you see by increasing the slag amount, the microstructure is getting more dense. And one more thing about here is the SI/AL plus Fe ratio, that's an indicator of how the geopolymer is good. Based on the literature, they say this ratio should fall between 1 to 3. If the numbers goes beyond these boundaries, the geopolymer probably will not be good. There are some rare cases that it's not true, this criteria, but most of the time it works. And we see that by increasing the slag amount, because the iron is more in the slag, it involves in the geopolymerization, it helps to produce stronger polymer networks, and also the SI/AL plus Fe ratio falls in the range, and that gives us a better geopolymer. Now, after you determining which percentage of slag is good, then we said, okay, now what about the temperature? How much heat we should expose these samples to, so the curing can be completed. So we put the samples in the oven from 60 degrees to 120 degrees Celsius, and we check the samples UCS, compressive strength, in 7 days. By checking this graph, we see that obviously there is an increasing and decreasing trend. That means by putting the sample, by increasing the temperature from 60 to 90 degrees, we are having a better geopolymerization. The strength is higher, but then we see a slight decreasing. Is there a specific reason for this? We are going to see in the microstructures studies too, but yes, there is a reason. With higher temperature, we are able to get more silica and alumina from the material. But as soon as we increase the temperature beyond a certain point, which is here for 90 degrees Celsius, then the water evaporates soon. The water from the alkaline solution evaporates soon. And that makes two things. First, the geopolymer gel that quickly started covers the other mine tailings, and the water evaporates, so we are not be able to go deeper mine tailings and then try to make the material take the silica and alumina out. And the water evaporates and more voids created in the sample that we are going to see in the microstructure level. And you see here in the graphs, by increasing the temperature from 60 to 90, it's getting more compact, but as soon as we go higher, we see more voids in the samples. And an interesting things here too. So if we go with a 90 degrees temperature, curing temperature, we see that the SI/AL plus Fe ratio is falling exactly in the middle of the range that we discussed, and it's providing a better geopolymerization that is good for producing durable construction material. Now we check the temperature and we check the slag content. It's time to check what should be the water content we should use, what is the right amount, and what compression or forming pressure we need to use. We check 3 water to solid ratios, and this water is just the water mixed with the alkaline solution, and the solid ratio is the total solid material that is available in the mix. So we use the 0.12 to 0.16 for the water to solid ratio, and then we try to put a pressure on the samples starting from 1 megapascal to 30 megapascal, and see how the compaction energy is helping us. Generally, with compacting more, the UCS is more. We are going to talk about it in the microstructure, that why this is happening. But what about the water to solid ratio? In lower forming pressure, just let's say 1 megapascal, because the compaction is not that much. By increasing the water to solid ratio from 12 to 14 to 16, the UCS is increasing. That means in lower compaction energy, the liquid is there, And higher liquid means we have higher amount of sodium hydroxide and sodium silicate. And when this is higher, the alkalinity of the media is higher, the pH is higher, then we can dissolve more silica and alumina from the mine tailings and slag. And then we can have a better geopolymer. But as we increase the forming pressure, if the water to solid ratio is too high, then during the pressure, the water is going to squeeze out, and you're going to lose your alkaline solution, and the UCS is going to be lower, which you see after 4 megapascal or 3 megapascal forming pressure. Then the liquid is starting to squeeze out, and the UCS is lower than 14% water content. If you want to check about the microstructure, this tree shows the forming pressure effects. So first with the 1 megapascal forming pressure, then 10 megapascal, and then 20 megapascal. And we are seeing that by increasing the forming pressure, the microstructure is denser and the UCS is higher. What about the water to solid ratio? At a constant forming pressure, if we are increasing the water to solid ratio, the porosity is increasing and the UCS is decreasing. But as we discussed in the graph that we showed, a good combination of the forming pressure and water to solid ratio will provide you a better cementitious material. Now we find that from the results of here, we decided to keep and try all of these samples for the water absorption, because we cannot just by this graph decide which one we are going to use, because even the high forming pressure is you're going to put more energy on this, and then probably this life cycle analysis is not going to work, and it's going to make like issues. So we need to check all these samples for other critical criteria and see which number we should go for. So we tried to do the water absorption test. Basically, we put all the samples in the water for 24 hours and then check the water absorption rate. And this graph shows by having a higher forming pressure, the water absorption is low. And obviously, yes, when you push the material harder, you compact them and the porosity decreases. So you have low porosity, the water cannot penetrate, the water absorption will be lower. And what about the water content? We see at higher water content, at lower water content, the material are more prone for water absorption because the water is low. So there is a potential for the extra water to go inside the microstructure and try to saturate the sample. And that's why the water absorption is higher. So the more water we have in the sample by itself, the less water absorption we will have. Then after water absorption, when the samples are wet, we take them out, we test them for the UCS. And also we let those samples to dry and then again test the samples. And this graph shows you the results. So these 3 graphs on the below side is for the samples that we take them out in a wet condition and saturated condition and just test for the UCS. And then we let them dry for 24 hours in 90 degrees Celsius. And then we try to test them again and see which samples are more durable when we are exposing them to the water. And we noticed that the samples that pushed with 20 megapascal forming pressure is giving us a more durable material with higher UCS. So we decided now that we are going to use 20 megapascal forming pressure, and the highest sample is 14% water content. So those are the criteria we are going forward. And why is this happening? Probably the 14% water content and 20 megapascal is this combination is a favorable condition that we keep all the liquid in the system, and at the same time we are compacting the material enough to have a better microstructure. With the samples, with this maximum sample we have, now we tested the samples for different curing times. But we didn't put the samples anymore in the oven. So all the results after like 7 days are for the samples that are stayed in the laboratory environment in just the room temperature. And you see, even in the room temperature, by the time we have some growth in the sample strength, and we tested the samples up to 54 days, and then we 56 days actually, and we have the result. So in 28 days, based on the ASTM standard, as if you remember, we had 20.7 megapascal for the requirement. We see that our samples at the optimum preparation conditions, we are reaching in 28 days for 24 megapascals, which means that we are meeting the ASM criteria in terms of the UCS, and we already meet the criteria for the water absorption, because in the water absorption, even if we go back, I think I missed this part. Yeah. So for the water absorption, the ASTM asking for 13.13% maximum, and our samples are generally below that. And the sample we had, 20 megapascal forming pressure and 14% water content, is only 9.2% of water absorption. So we are meeting the compressive strength criteria and also the water absorption. Now let's do some durability tests on the samples and see how the material are acting. So the first thing we did is the freeze and thaw cycle. So we put the samples in the freezer and decrease the temperature to the freezing point, and then we put the samples, take the samples out after 24 hours, and then we put them in a melting zone, and then we kept them in the water for 24 hours, and then we check for water weight loss. So basically, when the samples in the freezer and then take them out, we want to see if the weight of the samples are decreasing. That means if the materials are losing their integrity and we are seeing that the particles are washing away. We tested the samples for 10 weeks, and each week we did 5 cycles. So during the weekdays, we did the cycles, and then we did 50 cycles on the samples. And at 50 cycles, you see at each week, we are seeing a decrease in the weight of the samples. But what is the weight loss ratio? It's only 1.1% of weight loss after 50 cycles of freeze and thaw. And we did the ultrasonic testings on the samples to make sure if there is any crack developing inside the samples, because we are by just measuring the weight, it's not good enough to say that the materials are durable, which I mean is a good indicator, but we need to do more detailed study. And the ultrasonic velocity testing showed that the velocity of the wave passing through the sample is not changing that much during the freeze and thaw test. That means there is not much cracking, like major cracking, developing inside your samples. There are only few minor cracks on the surface of the samples, and it doesn't affect the integrity of your sample. So if we are passing the freeze and thaw test, what about if we put the samples just in wet and dry samples, like if the samples are saturated in water and then we dry them? So how about this? And we see that by just putting wet and dry cycles, doing the cycle 14 cycles, which means 14 days of saturation and 14 days of drying, the weight loss we have is about 7%. But the UCS, after we take the samples out and test them in wet condition, the UCS of the samples is about 7 megapascal. So the initial strength of the bricks are 24 megapascal, but they are not losing, they are not washing away, they are keeping their strength, and the 7 megapascal is very comparable to the cementitious material. This graph shows the microstructure level. So before wet and dry cycle, and then after 14 wet and dry cycle. And you see in the microstructure level, the only thing that is changing majorly is that the sodium hydroxide, some of the sodium hydroxide that are not participated in the geopolymerization is washing away. So this is mainly the main reason that the samples are reduced, the strength of the samples are decreasing. And if we check the XRD patterns of the samples, we see that the crystallinity of the material is there. And obviously, geopolymerization is good. We could say for the geopolymerization, we could talk about the area below the graph, below the patterns, so the area between these dashed lines and the XRD patterns. So the geopolymerization is strong. Now, the environmental test. We put the samples in two different liquids. So one was just the normal water, and then the other one was acidic environment. And also, we put the powders in the same condition to make sure if the geopolymerization is really successful or not. So this test, the samples are soaked in water for 120 days, so actually like about 4 months. And then after that, after 4 months, we take the liquid out and we did the ICP mass testing on the samples. And here are the full results. Just let's see the mine tailings and slag powder. The heavy metals are very high, higher than the EPA limits. If you see, for example, for the zinc, we have 24. We have for selenium, for cobalt, for nickel, we have higher numbers. But what about the geopolymer samples? They are very stable and they are below the EPA limits. So that means we are able, with the geopolymerization, we are able to stabilize the heavy metals inside the geopolymer matrix, and that's what we want. So as a conclusion, we were able to produce bricks with the mine tailings and with the help of definitely slag cement, and that's and passing all the ASTM criteria. The future work we need to do is to do life cycle and techno-economic analysis on the bricks and see if we can economically produce these type of bricks. We did very small, very small mathematical analysis, and we saw that by producing 6 million of bricks annually, we can the profit will be about $400,000, just the profit, and the price of the bricks are cheaper than the price of the bricks that you can find in Home Depot and these stores. So we did very small minor studies. I didn't provide the results here, but to produce them as a pilot, we need to do some life cycle and technical analysis. If you want to read more about this research, I would encourage you guys to read these two papers that are exactly from this research. We also did some research on using slag cement to produce some binders for the pavement industry with my colleague Lina Mann-Harris and Dr. Chang as our supervisor. And this is also a good paper to go and review it in terms of like pavement research. Thanks. I would like to thank BHP for the funding provided for this research and access to the abandoned tailing dams to get the tailing samples. And at the end, thanks to the Slag Cement Association for this opportunity. And here is a question and answer. Thank you.
Thank you, Arash. We'll now be taking questions, since it looks like we have one right now. The question is, does a relatively high level of alkali required to activate the geopolymerization process place a limit on what aggregates can be used due to concerns for ACR?
Alkali silica reaction, if the main concern is about alkali silica reaction, in the microstructure level, we didn't see much of the alkali silica reaction, but we don't want to go with very high number in alkalinity. No, really, we produce samples even with 5 mol, 10 mol, with 5 mol and 7.5 mol. So there is no reason to go very high limits. The reason I provided the 15 mol sodium hydroxide results is just those results were in the initial state of trial and error in their experimental research that everybody do before getting an idea where to start the points of the research or where to design the experimental program. So that's why we put some, we use higher alkalinity. But no, based on the ACI, we didn't see alkali silica reaction in this samples, if that answers the question.
Perfect. If you have any other questions, please let us know. Looks to be everything right now. If you do have any other questions later, you can contact me. You can contact SCA at info@slagcement.org, and we can answer your questions there. Also, if you want to have access to the webinar, it should be live on SCA's YouTube channel and on our website in the coming days. So please keep an eye. Oh, we do have another question here. Did you have any afluorescence testing on the bricks?
I would say just with some observations, if we use higher alkalinity in the samples, like 15, we had some influence just by observation. No, we didn't do the testing, but sometimes you see, like just by taking the samples out of the wet and dry cycles, or even like after curing it off, and we had some samples with high alkalinity that had some effluence, but no, we didn't do the testing actually.
Perfect. Well, everyone, I want to thank Arash again for presenting today, and I want to thank all of you for attending as well. And like I mentioned, yes, this webinar will be on our website and our YouTube channel if you'd like to view it later. Thank you, and
Thank you, everybody. Thank you.
Bye, everyone.